Hey everyone, welcome to our next installment on acid-base chemistry as it relates to organic chemistry. And we talked a lot in the previous lecture about pKa and gave some useful benchmark values. But what do you do if you don't know the pKa of something? And that's going to happen. The thing is, even if you wanted to know every single pKa, you probably couldn't. Some of them haven't been measured, and it's just too many to memorize. I don't even know them all, and I'm a chemist. So you absolutely don't need to know every pKa value you can find. What we do instead is we try to promote an understanding of what creates acidity, and then you can use that understanding to basically make a guess about a compound's pKa. So you're not just going to randomly guess, right? You're going to make it an educated guess using some tools that we have in our toolbox. So one of those tools is our pKa benchmarks. Those values you should know, and they'll again give you a jumping off point to say, oh, this looks kind of similar to that, which I know has a pKa of 10 or 5. So you can kind of get a place to start and then move up or down. And then the other part that's new today is we're going to talk about some different things that make alcohols, carboxylic acids, any kind of acid functional group more acidic. So this is what we call structure acidity relationship. But that's kind of a mouthful. So I just like to call them the 4 factors, because that's a lot easier and quicker to write. So through these 4 factors that we'll talk about in this video, you'll be able to get a sense for the stability of a compound. And so we'll talk a little bit at the end about what that means regarding acidity, but these factors that tell us about the stability of something will tell us if it's really stable, it's not going to be reactive. And if it's not stable, then it is probably pretty reactive. So let's go through our different factors here. We'll list them out and then we'll talk more about each of them in detail. So the first factor is different elemental factors. There's a couple of parts to this, but based on the element that you're looking at, we can tell some things about its stability. The second one is hybridization. So what hybridization state an atom is in will definitely have an effect on how acidic it is. The next one is induction, which may be a familiar term, but that's going to have to do with what else is nearby that can help draw electrons to itself. And the last one is resonance, which is sort of similar to induction in that it's talking about what's nearby that will help basically stabilize a charge. So we'll get more into those two toward the end. Let's start with the elemental properties. So in elemental properties, like I said, there are a couple of different pieces. The first one is electronegativity. So in the case of electronegativity, we have some values in the back of our mind, hopefully, and if you don't, look them up for practice. When we look at an acid-base question, we're going to see an atom that either has an acidic hydrogen on it or maybe has a charge, right? So in this case, I'm going to talk about looking at something that has a charge on it. If that atom has a charge, we want to ask ourselves, okay, is that a very electronegative atom or not? Is it happy, quote unquote, with that charge? So electronegativity of an element will mean if it's high, that element likes to have a negative charge to it. So the example that I like to give for this one is if you have a carbon with a negative charge compared to an oxygen with a negative charge, the oxygen has the higher electronegativity value. So between these two, the oxygen is more stable. So that's how we can compare two different elements to one another and think about their stability, particularly when they're bearing a positive or negative charge. The next part is size. And there's a little caveat here that size does vary across a row in the periodic table, but when we're comparing things that are all in the same row, like carbon, nitrogen, oxygen, the differences aren't big enough to really matter. So when we're comparing size, we only want to compare the size of two elements that are in the same family. And so just as a refresher for what that means they're in the same column of the periodic table going downward, right? So we have carbon, silicon, et cetera, et cetera. You're probably not going to see anything lower than silicon, right? But things that are in that vertical column in the periodic table. So my example for this one, and this is probably the most common one that you'll see anyway, is comparing an oxygen atom to a sulfur atom. And, you know, they could have negative charges on them as well, but they're in the same family. Sulfur is right below oxygen, and therefore sulfur has very similar properties to oxygen, except it's got this whole extra, you know, set of electron shells that are filled, and that makes it bigger, right? So as we go down a column, right, or across the opposite direction in the periodic table, atomic size gets larger. What this means is that if we have a big atom, that means just a bigger area for electrons to float around in. They both have a -1 charge, but sulfur can distribute that negative charge over a much bigger area than oxygen can. So picture trying to fit, you know, some number of electrons, an arbitrary number of electrons on, say, a golf ball, right, compared to a basketball, right? Or, you know, one of those big balls that you like a big old inflatable beach ball, that kind of a thing. That's the kind of comparison that we're making. If you're spreading them out on a bigger surface, they can get further away, and that's more stable. So in the case of size, sulfur is going to be the more stable of these two. Okay, so the next factor is hybridization. So we reviewed this earlier on in the semester to talk about what are these hybridizations, what do they mean? So we have these three options available to us. And again, a little caveat is that if we're comparing hybridization, the difference is only going to be big enough when we're comparing the exact same atom. So we'd be comparing sp3 carbon to sp2 carbon to sp carbon, right? If you're changing across elements, other factors like electronegativity are going to make a bigger difference. So we only want to compare hybridization when we're looking at the exact same element. So for that, there's a little bit of another tie-in here based on electronegativity. That's where this trend comes from, is actually from electronegativity. So the thing here is that the s orbitals are actually different in electronegativity than the p orbitals. S orbitals are more electronegative than p orbitals. So it's kind of weird because you just think of them as empty shells that are meant to hold things, but based on the spherical structure of S, that is what makes it more electronegative than P. And you don't really need to know why that is. If you're curious, we can talk about it sometime. But suffice it to say that if something has a more S-heavy hybridization, then it's going to be a more electronegative hybridization. So what do I mean by that? If we look at the content of an sp3 orbital, right? There's 4 things in there. There's 1 s and 3 p. That means it's 25% s and 75% p. So it's much less s than it is p. If we go to the sp2, now there's only 3 orbitals in there. So that means that it's, 33-ish% s and 66-ish% p. Getting into basically, this is what we call having higher S character. And so the case of SP, can't go wrong there. It's 50% S, 50% P. So when we look at it in terms of percentage of S character, we can find that our sp3 orbitals are the least electronegative, right? So our electronegativity increases going this way. So sp orbitals are going to be more electronegative and therefore more stable when they have to hold on to something like a negative charge, right? Electronegative atoms or orbitals want negative charges. So let me write that here in a different color. So sp orbitals are going to be more stable when they hold on to a negative charge. So this also can go in the opposite direction, right? If you have an atom that has a positive charge on it, right, that it would be really bad for an sp orbital because it's extra electronegative. If we have to have a positive charge somewhere, we would more want to favor that on an sp3 orbital because it's less electronegative. So this is where I say a little bit of that mind-melting nature of acid and base. Things go hand in hand, and there's two sides to each of these coins. So take all this in, let me know what questions you have about it, and we'll start to see a little bit more of how this can work in practice in a couple examples later on. But here's one quickly at the bottom. If we're comparing these two nitrogen atoms here and evaluating the acidity of those hydrogens, we could say, all right, this one here is an sp3 hybridized nitrogen compared to this one, which is sp2 hybridized. And if those were the only other factors at play, we would say, okay, that sp2 hybridized nitrogen has higher orbital electronegativity and therefore would be much more favorable to give up this proton than it would be to give up that proton. So again, in this case, this one would be the more stable with the negative charge after the hydrogen is removed. Okay, moving right along to factor number 3, induction. So you may have heard like an induction range or stove, and that means something a little bit differently from like electrical engineering and physics. So if you know anything about that, throw it out for now. When we talk about induction in organic chemistry, we're talking about a pull of electrons, right? And maybe this does have to do with the electrical engineering, but again, that's not our interest. We're going to try to be pulling electrons not so much through a stove to create like heat, we'll be pulling them through sigma bonds. And so specifically that means only single bonds, no double, no triple bonds. We're pulling the electrons through these bonds, and that can act as a form of stability. Okay, so let me give a goofy example, but this is one of my favorite examples. I drew this really, really bleak pool scene here. This is a pool because it's, you know, it's the end of summer. It's kind of hot, right? So let's say that it is pretty hot, and this is you up here, Chem 210 student. It's hanging out up here on the balcony, and you're like, hoo-wee, it's hot up here. I don't like feeling so hot. I'm unstable feeling hot up here. And then there's me, and I'm over here, you know, with like my arms behind my head. I'm just chilling on my pool lounger here, and I'm totally not paying any attention to the fact that I've got this cup here with some delicious iced tea in it. And you're like, man, if I could only get some of that iced tea, I'd feel so much better. I'd feel more stable about, you know, the heat out here today. So what induction is like is if you were to take a really big, super insane, crazy straw, right? And like reach it all the way across the pool and dip into my drink, right? And then pull that drink through the straw and into your mouth to enjoy the iced tea, right? So that's kind of like induction. You're pulling electrons through these pi bonds at a distance. So the straw here is kind of like your, I'm sorry, did I say pi bonds? I meant sigma bonds. Pulling through these pi, I did it again. Third time's a charm. Pulling through these sigma bonds, right? The straw is like the sigma bonds, and you are pulling the electrons or delicious iced tea to you through the sigma bonds. So a more kind of concrete chemistry example of that would look something like this. If you had, say, an alcohol, like so, we have a vague acidity value for that in our minds, hopefully from pKa. Pull it out, see what you think it is quickly, test yourself. And then if we compare that to an alcohol that's almost exactly the same in structure, but now we start to put some other groups nearby, you know, it doesn't have to be exactly right next to it, but some groups that are nearby. So what I like to think about when I talk about induction is this kind of a concept of thirst. It's a little bit cheesy, right? But fluorine is super duper electronegative, the most electronegative thing there is at about 4 on the electronegativity scale. So what that means is that it is strongly pulling a dipole to itself because it wants those electrons. It's really greedy. It's thirsting for those electrons. Same with this one here. And so what that means is that we have a big partial positive charge on that carbon that they're directly attached to. No big deal. But if we think further in dipoles, that means that this partially positively charged carbon is electron deficient, and it wants to get some electrons for itself too. So it's actually pulling its own dipole. So it's a little small. Let me draw that again down here. It's drawing its own dipole away from this carbon because that has some electron density it can spare. So it's going to pull that way on it. And similarly, it's going to want to pull a little bit on that oxygen. Of course, the oxygen is pulling on it in its own way. But if we imagine that we take off both of these hydrogens here for a moment and give these oxygens negative charges, now some of this electron density that's sitting here on this oxygen can be kind of pulled upon by these fluorines over the course of these sigma bonds, right? So the fluorines kind of help pull a little bit of that away from the oxygen to stabilize it. Whereas in the case of this molecule on the other side, we don't have that stabilization. So in order to have this induction, you need to have some kind of electronegative atoms. And in our case, it's almost always going to be fluorine or chlorine. Anything else is probably not really electronegative enough to do a whole lot of induction. You may see oxygen, but these two are more common. So you have to have those electronegative atoms, and they must be probably no more than 3 to 4 bonds away from something that has a charge on it. Because if they get too far away, then, it's like you're not going to be able to get a crazy straw that long. So there's really no stabilization after they get maybe 5, 6, 7 bonds away. If we count up how many bonds we have here, so there's the fluorine, we'll count from that one. There's 1, 2, 3 bonds. So we're well within the ability for those to inductively withdraw the electron density away from oxygen and toward themselves. So yet again, this version here is going to be the one that is more stable with the negative charge. Should write in here negative, because again, the flip side of the coin is still in play. If this was for some reason a positively charged oxygen, those fluorines there would actually be bad and they wouldn't be helping. So it's important to think about this side of the coin and then the other side of the coin that I'm not going to spend as much time on today. So the last piece of our 4 factors is the resonance piece. And so you may or may not have encountered any resonance in your studies before, but resonance is a really big deal in organic chemistry. It's a great way to achieve stabilization. So let's talk about it. I'm going to go briefly over it here, but I will recommend a couple of other videos that I've already prepared about resonance to help you get a little bit more familiar with it, because it is a tricky concept that a lot of students struggle with. And I just want to introduce it here in the acid-base department, and then we'll think about it more and practice with it more over the course of the whole semester. So what is it? What is resonance? It is another method of sharing electrons, right? But this time it's going through the pi bonds that I was so eager on the previous slide to refer to. This time it's pi bonds. Induction is strictly sigma bonds. So the term resonance itself, you can think of kind of something that resonates, sort of a going back and forth, right? The resonating or resounding, that's what's going on here. It's kind of a back and forth. So what I will do here is use my same bad example of the hot summer day by the pool, right? You gotta get some water in that pool, otherwise it's no fun. So let's say that we have the same situation. You, wonderful Chem 210 students, are up here on the balcony and it's still hot and you're still not happy about it. And then I'm over here still lounging on my chair, getting my tan, all that kind of thing. There we go. So instead of the crazy straw right? Because that is one way, but there are other ways that we could instead share this iced tea that I've got here. So let's say that this is a can of iced tea, a nice closed can of iced tea. So resonance would be more like, oh, I hear you over there saying that you are thirsty and that you wished you had some iced tea. So what I do is I just throw you the iced tea up to the balcony, right? And it could be even a different situation where, say, you're not quite so hot this time, but now I'm hot, right? And I could use some iced tea. Maybe you have a cooler full of iced tea up here that you'd be willing to share with me. So you could, that's supposed to be it's a three-dimensional cooler there. So if you had the iced tea and instead I was the one that was looking for some iced tea, you could throw an iced tea down to me. So this is kind of the throwing it back and forth or resonating idea that we can share it basically over through space, kind of, right, through these pi bonds. So it's not directly through a sigma bonding framework, it's through space using pi bonds. So an example of this will look something like, what do we want to do? Let's do, this is going to be a very simple example of resonance, right? Just to show resonance, not so much acidity first. But we can do it. We can do a little bit with acidity. So this is a carboxylic acid, right, where we've lost the proton. So we can think about, all right, this oxygen here, that's the one to focus on when we're looking at stability, right? We want to evaluate how stable is that oxygen when it holds on to that negative charge. And that's all good and fine. But the other thing is that we're allowed to resonate this negative charge up to this other oxygen here because we have the exact right arrangement of bonds. So in order to have the right arrangement of bonds for resonance, you have to have a single bond and then a double bond or triple bond. So again, I'll refer you to some other videos that you may want to look at to get a little bit better of an idea about what resonance is and how to draw it. But the point being here is that this oxygen has extra electrons, right? It has 3 lone pairs instead of just 2. So these electrons can kind of go down like this to form a new bond along this oxygen-carbon bond. And then we're going to break this pi bond and actually put it up atop here where those other lone pairs are. And then after you've drawn the resonance, it'll look something like this. And now that red lone pair of electrons is up on that top oxygen and the negative charge as well. Let's not forget that. So this does look kind of like, oh, you took the same thing, you just turned it. And that's true in this case, but even if we said, okay, we can go in, chemically speaking, and do a special radioactive label on each of these different oxygen atoms, if we did that experiment, we'd still see, yeah, okay, some of the time the radio labeled one has a double bond and some of the time it has a single bond. So what this means is basically that we're just able to share this negative charge worth of electrons between 2 different oxygen atoms. And again, what this gets at is similar to the idea of having a bigger elemental size. The more distance, the more space you can spread electrons out over, the more stable it's going to be. So if we had, there's probably not really a super great analog to this, but if we had this alcohol compared to the carboxylic acid above, right? Thinking that they are fairly similar if you ignore this carbonyl that's here, right? Comparing the acidity of those, especially if you have the 2 benchmark values in mind, there's a 10 pKa unit difference between them. And that has everything to do with the fact that resonance is available to help stabilize this negative charge that we create. So when we're looking at, again, comparing these 2 directly to one another, the carboxylic acid is going to be more stable with the negative charge than the OH by itself would be. Okay, So there's a very quick primer on resonance and what it means to resonate. Now we have to kind of step back and think about everything that we've talked about. So we've learned what the four factors are and how they can kind of help us decide between, if we're looking at two different things, we can help decide which one is more stable. And that's basically what you're going to be doing in the acid-base chemistry unit. You're going to be comparing two things and deciding which one is more stable. So this amount of stability relates to how acidic something is. And so this is where it gets a little funny, but when, at least personally for me, when I am evaluating acids, what I prefer to look at is the stability of its conjugate base, right? Because conjugate bases are going to be the things that have negative charges. And as you can see, the way I framed these factors is around negative charges. Again, if you prefer to think about it in the opposite direction, it totally works. You just may want to ask me some questions about it. So if that seemed better for you, please reach out. What I'm going to look at is how stable a conjugate base is, and we'll do a practice with this in a moment. But if a conjugate base is really stable, that means, oh yeah, it was no problem for it to give up the proton. So that means it came from a really strong acid. Whereas if you were to make a conjugate base and you're like, oh, wow, that doesn't look so good, it doesn't have any stability to it, then it's less likely it's going to want to give up that proton, and it's probably going to be a weaker acid. The other takeaway that you should know is that all of these four factors are important. But that said, if you have a great ability to resonate, resonance is often going to be a dominating factor when it's present. So if, for instance, you have, let me do a little generic example. If you have this conjugate base with no resonance, and you're comparing that with the base that has resonance to stabilize a charge, the one that has resonance is often going to win out. Now, that's not always going to be the case, but if there's no resonance in one and there is in another, it's more likely than not going to be the one that has resonance. Now, what'll be a different exercise is when you have to compare a conjugate base that has no resonance to a base that has no resonance. Or if they both have resonance, then the other factors are going to kick in a little bit more to help you compare to decide which one is more stable. All right, so let's sit with these takeaways for a moment, and then we'll move on to using these factors to help us predict pKa and to do those acid-base problems that you all know that I love. So take a little break, ask some questions, think about these factors, read it up in your textbook, and then move on to the second video where we'll apply these factors to some different pKa and acid-base related problems.